Hello, everybody, and welcome to the solutions to Quiz 2. This is from the spring 2023 semester at Cal State Fullerton. This is Math 302, Modern Algebra, and this is our first problem. So let's jump into it. We're given a relation, call it R, on the plane R2. So this is the Cartesian product of R with itself. And so we want a relation from R2 to itself. And the way we're going to define it is if you have 2 points in the plane, so A comma B, okay, this is an element of R2, and then C comma D, this will be another element of R2. And we want to know whether or not they're related, quote unquote, right? Meaning that this pair of elements from R2 is in the relation R. And the answer is it's going to be in the relation R if, and then here comes complicated expression. Okay, so you compute some weird formula, and it's supposed to be less than or equal to 1. And then we're asked to determine if this relation is actually an equivalence relation on the plane. Now, before we just jump into the algebra of this, why don't we look a little bit at this obscure, bizarre expression here, because if we do, we might notice that it's not as bizarre or obscure as we thought. So first, there's a square root of a sum of squares, and that should put into your head something like the square root of x squared plus y squared, some sort of formula like this, which you see coming from the Pythagorean theorem. So if I have a right triangle with side lengths x and y, and I want to know the length of the hypotenuse, this will be the square root of x squared plus y squared. And the length of the hypotenuse, another way of saying it is that's the distance between these 2 points here, right? So if this was like a point P and this was a point Q, then this square root of x squared plus y squared is the distance between P and Q. And that distance word should make you think of the distance formula, and then you go back and go, wait a second, isn't this exactly just the distance formula for these points A, B, and C, D? So what we could really be saying here is that the distance between the points A, B, and C, D is less than or equal to 1. So we're really just saying that 2 points are related if they're less than or equal to 1 apart. That's it. And this should make checking whether R is an equivalence relation a lot easier. So let's do it using this nice interpretation. Then I'll show you how to do it just algebraically, pretending you didn't know what in the world we were even talking about. So first, I'll check reflexivity. So for reflexivity, I need to test a single point, see if it's related to itself. So I look at some point A comma B, and I want to know, is it related to itself? All right, so is AB in R? Well, it is if AB and AB are less than or equal to 1 apart from each other. And of course, they're 0 apart from each other. They're the same. Right? So the answer here is yes, since they are 0 apart. Okay, fine. How about symmetry? Well, this shouldn't be so bad. So now we're going to assume that I have 2 points, AB and CD, that are in, that pair is in R. But this just means, right, that they are less than or equal to 1 apart. But distance apart doesn't depend on which one you say first. If I ask how far apart P and Q are, it's this same answer, this root x squared plus y squared, as if I said how far is Q from P, right? Distance doesn't care which one you start with first. So this implies that CD and AB are less than or equal to 1 apart. So this implies that CD and AB, that pair is in R. So we get symmetry. Finally, we'll check transitivity, right? We're feeling pretty good about it, right? Well, let's see. So if I have a pair AB and a pair and a CD, which are in R, so that means they are less than or equal to 1 apart. And if I know that CD and say a point EF are in R, so that means they are also less than or equal to 1 apart. Does that mean that AB and EF have to be less than or equal to 1 apart? And here the answer is going to be clearly no. And let's just draw a quick picture. Okay, so here's going to be a circle with radius 1. And let me just stick AB at the center of the circle. And I'll put CD on the perimeter of the circle. All right, but now let me draw another circle with radius 1 with CD at the center. Okay, so I can come over here, another 1, and then I get to put EF on the other end. And now we can see that the distance from AB to EF is 1 plus 1, which is 2. So AB and EF are not less than or equal to 1 apart. So in fact, what I can do is write down an explicit example of this. Okay, so I'm going to take AB to be 0, 0. And I'll take CD to be, well, let's just move over 1 to 1, 0. They are 1 apart. They're exactly 1 apart, so that pair is in R. But now also, if I take 1, 0, and we'll just move 1 over to the right, and 2, 0, they are also 1 apart, and so that pair is in R. But if I look at 0, 0, and 2, 0, those are 2 apart. And so this is not in R. And so transitivity fails. Which implies R is not an equivalence relation. Okay, so this is probably the ideal way to do it. But maybe you didn't see that. So what if we were going to do this algebraically, right? Well, algebraically, we would have started, all right, let's do the algebraic version. Maybe we would have started with reflexivity. And we said, okay, we're going to look at AB and AB, and we want to ask, is this in R? And so I would now have to check A minus A squared plus B minus B squared, and then square root that, and say, well, this is 0, and this is 0. Square root of 0 is 0, and that's less than or equal to 1. And so the answer is yes. Okay, and that's how we would do it. And we would do it for symmetry and work the same way. We would try it for, I'm just going to skip the symmetry one, because you can kind of see how it's going to go. But let me see what would happen if we tried transitivity. So if we started off by assuming that A, B, and CD were in R, and that CD and EF, that pair was in R, then I would know that the square root of A minus C squared plus B minus D squared is less than or equal to 1, and that the square root of C minus E squared plus D minus F squared, that is also less than or equal to 1. And here's where we would be sort of stuck, right? We can now ask, well, what happens when you do the square root of A minus E squared plus B minus F squared? And we could start expanding this, right? And we can expand all these things. But we're going to run into some problems, as the previous fail of transitivity showed us. But let's say you just messed around with this, right? Like, for example, I might square everything up here, right? Just we can get rid of all these square roots. I say, okay, I have A minus C squared plus B minus D squared. That's going to be still less than or equal to 1. And C minus E squared plus D minus F squared, that's less than or equal to 1. Well, I want to combine these somehow, but a reasonable way to combine them is to add them. And if I add them, I'm going to end up with, well, let's see. I could distribute just everything I see. So like A squared minus 2AC plus C squared plus b squared minus 2bd plus d squared. Then we'll do all the bottom stuff, plus c squared minus 2ce plus e squared plus d squared minus 2df plus f squared. And that's all going to be less than or equal to 1 plus 1, which is 2. And you could see where we're going to run into a little bit of a problem, because there's not really a whole lot of cancellation or simplification that we can do here, right? We have a little bit, right? We could say, okay, well, let's see. I have an a squared. I have 2 copies of c squared, right? So plus 2c squareds. I have a b squared. Okay, here, maybe we'll write this in letter order here, right? Alphabetical order. So I have 2c squareds. There's our b squared. We have 2 d squareds. Fine. Let's see. There's an e squared. Let's see. I guess, yeah, we just get the 1 f squared. Yep, so there's an f squared. And then we got a whole bunch of other stuff. So minus 2 copies of ac and bd and CE and DF. Okay. And this is all less than or equal to 2. Now, the thing we're really trying to get at, right, we would want this to be less than or equal to 1, or equivalently, a minus e squared plus b minus f squared should be less than or equal to 1. And if I distribute things on the left, I get a squared minus 2ae plus e squared plus b squared minus 2bf plus f squared. All right, so this is happening if and only if. And I don't have any good way of using what I have up above to get down to the 1, right? I could, like, if this is going to be less than or equal to 1, then we could pull out. We don't even have all these terms, right? Like, we're just kind of stuck here, right? We got nothing that we can do. And that's when we should think maybe this is false, right? So we do all this work, right? We're doing all this algebra, and nothing seems to be falling out. That's where we think, well, maybe we should try to look for a counterexample, all right? And we saw up above, the counterexample is not all that complicated, right? We just take 3 points that are in a straight line. Okay. So the algebraic approach, of course, right, isn't going to fail you for the reflexivity and the symmetry. The transitivity, you just get stuck, okay? But in all these cases, do you notice, once you have this nice interpretation in terms of distance, man, does this just get a lot easier, a lot more conceptual, right? And it's easier to put together an example. So the big takeaway from all this is, try to come up with a good interpretation of a formula that you're seeing. If you can come up with a geometric idea, that often can be just invaluable in trying to understand what's going on without having to necessarily do all of the algebraic manipulation. All right, we'll see you next time with problem 2.